In our last class, we introduced a new circuit analysis technique called Thevenin's theorem, in which you could take a circuit of arbitrary complexity that connects to another part of the circuit at two different terminal points and replace the part of the circuit that you want to model with a voltage source and a series resistance. And we call that Thevenin's theorem. And we looked at different ways to finding this resistance that is part of the Thevenin equivalent circuit. We started with a very easy method, which was called the equivalent resistance method, which was limited to circuits that had independent sources and resistors only. Then we looked at another method called the VOC-ISC method, where VOC stands for open circuit voltage and ISC stands for short circuit current. And we saw that that method is more versatile and that it can also work with circuits that have dependent sources. We then introduced a third way to find the Thevenin equivalent resistance, and that was called the external stimulation method. In the external stimulation method, we applied an external voltage source or current source and then measured either the current coming out of the voltage source or the voltage across the current source, and we used that measurement to find the Thevenin equivalent resistance. When we introduced that last method, I mentioned that what makes it better than the other methods is that there are some circuits for which neither the equivalent resistance method or the VOC-ISC method works. And we're going to look at that now. Specifically, we're looking at the Thevenin equivalent model for source-free subcircuits. So a circuit is considered source-free if it does not have any independent sources. In other words, if it consists only of resistors or resistors and dependent sources. The problem with source-free subcircuits is if you try to calculate the open circuit voltage, you're going to get 0 volts, and if you try to calculate the short circuit current, you're going to get 0 amps. So if you have dependent sources but no independent sources, you cannot use the equivalent resistance method because of the dependent source. But if there are no independent sources and VOC and ISC are both 0, you cannot use the VOC-ISC method because you end up dividing 0 by 0. So that means that if you have a circuit with dependent sources and resistors but no independent sources, you must use the external stimulation method. Note that if you have a subcircuit that only has resistors, no sources at all, you could use series and parallel combination of resistors in order to find the Thevenin resistance. But we're talking specifically now about circuits that do have dependent sources but no independent sources. So for these, we have to use the external stimulation method that we started talking about last lecture. So to review that, you apply either a current source and then measure the voltage across it and notice the orientation of the plus and minus for the external voltage you're measuring. Or you apply an external voltage source and you measure the current leaving that source. Once again, note the direction of that current that you're measuring. And in both cases, the Thevenin resistance of this subcircuit that you're modeling is the ratio of the external voltage to the external current. Let's illustrate with this an example of a source-free circuit. Notice this circuit is source-free because it has no independent sources. It has a dependent source, but that does not count as far as Thevenin equivalents go. Because it is source-free, what this means is that the model for this subcircuit is nothing more than a Thevenin resistance. Because if we were to measure VOC, we would see that it was 0 volts. If we were to measure ISC, we would see that it was 0 amps. So the Thevenin equivalent is just a resistance, and the only way we can find it is through this external stimulation method. So let's apply that. We have our dependent source, and its value is alpha Vx, where Vx is the voltage across this 6 ohm resistor on the right here. 2 ohm resistor there. There's our Vx, which is the voltage across the 6 ohm resistor. And we have a third resistor here, 3 ohms. So we're trying to find the Thevenin equivalent of this circuit. And the way we do it is we have to apply an external voltage source or current source. I will apply an external voltage source. I'm going to make it 1 volt. And I want to measure the current leaving that source that I'm applying. I call it I external. Recall when you use this external stimulation method that if there were independent sources in the circuit that we're modeling, you would turn those off at this point. Because there are no independent sources, there's nothing to turn off, and we just need to evaluate the circuit here. So to analyze this, let's call this point ground, and we'll call this voltage Vx since it's already given. And let's do KCL at the Vx node. That current plus that current plus that current has to equal 0. Current to the left, Vx minus alpha Vx over 2. Current going down from Ohm's law is Vx over 6 ohms. The current going to the right is Vx minus 1 over 3, and that sum has to be 0. Let's factor out Vx. You get Vx times 1/2 minus alpha over 2 plus 1/6 plus 1/3. And on the right-hand side, all that we have is a 1/3. Getting a common denominator of 6, here we get Vx times 3 minus 3 alpha plus 1 plus 2 all over 6 equals 1/3. Solving for Vx, you get Vx is equal to 2 over 6 minus 3 alpha. As expected, the value of Vx will depend upon the value of alpha, which is the parameter in this voltage-controlled voltage source. What we're looking for actually is I external. I external, this current here, from Ohm's law, is 1 volt minus V sub x over 3 ohms. We plug in the value for Vx that we determined down there, and we get 1 minus 2 over 6 minus 3 alpha all over 3. So the numerator, getting a common denominator within the numerator, we get 6 minus 3 alpha minus 2 all over 6 minus 3 alpha divided by 3. You work out the math, you get 4 minus 3 alpha all over 18 minus 9 alpha. Finally, the Thevenin resistance is what? The external voltage divided by the external current. The external voltage was 1 volt. The external current was this expression here. So we get our final answer, 18 minus 9 alpha over 4 minus 3 alpha. And that is the value of this resistance. Once again, because we have only resistors and dependent sources, the only method that we can use is this third method, this external stimulation method, because this is what's called a source-free circuit. Let's just look at this problem a little bit more, and let's see what happens for a couple different values of alpha. What happens if alpha is 2? If alpha is 2, the Thevenin resistance is 18 minus 9 times 2 over 4 minus 3 times 2. I'm just plugging in alpha equals 2 into this expression there. You end up getting 0 ohms. So for this particular value of that parameter, the Thevenin equivalent resistance is 0. It's a short circuit. What happens if alpha is 4/3? Now the Thevenin resistance is 18 minus 9 times 4/3 all over 4 minus 3 times 4/3. You do that, you get a resistance of infinity, which is an open circuit. So once again, by changing the value of this parameter here, you can turn the resistance all the way from a short circuit to an open circuit. But we can get something even more interesting here, and this is because this is a dependent source. Suppose we were asked to find for what values of alpha is our Thevenin negative. Basically, we want 18 minus 9 alpha over 4 minus 3 alpha to be less than 0. This expression is less than 0 in two situations. The first situation is if the numerator is negative and the denominator is positive. Solving for this, 18 minus 9 alpha less than 0 is the same as saying alpha is greater than 2. 4 minus 3 alpha greater than 0 is the same as saying that alpha has to be less than 4/3. Turns out that you cannot simultaneously have alpha greater than 2 and alpha less than 4/3. So this gives us an empty set. But you can also get this expression here to be negative if the numerator is positive and the denominator is negative. So the alternate approach is to make the numerator positive and the denominator negative. Let's solve these inequalities. First inequality is the same thing as saying that alpha is less than 2. And the second inequality, solving for alpha, you get alpha is greater than 4/3. What this means is that if alpha is between 4/3 and 2, we get a negative resistance. So although you cannot actually buy a negative resistor, what you can do using dependent sources, such as op-amps, you can actually create a circuit that models a negative resistance. Now, why you would ever want to do that is beyond me, but this is showing that at least mathematically you can do that. We're now ready to cover the fourth and easiest way to find the Thevenin equivalent model, and this is using the source transformation which we learned a few lectures ago. So it happened in some cases we could do subsequent operations of source transformations in order to simplify a network to its Thevenin equivalent without doing much work at all. I should point out that this method is valid only if the subcircuit contains only independent sources and resistors, and even then it's not always possible, because if you remember, just because you have a circuit with independent sources and resistors, there's not always source transformations that you can do that can make the circuit simpler. But let's show how source transformations can be used to find the Thevenin equivalent of this subcircuit to the left here. So we're going to start by taking this voltage source in series resistance and converting it to a current source in parallel resistance. So 20 volts and a 5 ohm series resistance is equivalent to a current source of 20 divided by 5 or 4 amps with the parallel resistance of 5 ohms. We stick that back into the circuit now. 4 amp source, 5 ohm of parallel resistance. Stick that back in. So we have our 2 amp source here. And our 20 ohm resistor. Now we can combine this 4 amp and this 2 amp source, and we can combine the 5 ohm and the 20 ohm resistor. 4 and 2 give us 6, so we get a 6 amp source. The 5 ohm and the 20 ohm resistor in parallel, 5 in parallel with 20 is 4 ohms, and so we get a 6 amp source and a 4 ohm parallel resistance. Finally, we can convert this back to a voltage source and a series resistance using another source transformation. The voltage source is 6 amps times 4 ohms, or 24 volts. And the resistance is a series resistance of 4 ohms. And this is the same Thevenin equivalent circuit we saw earlier when we found the Thevenin equivalent using another method. So clearly, the source transformation method is easiest because first off, notice we don't have to separately find VOC and R Thevenin. We get them both together, and you can get it just from simple source transformations. The problem, of course, is that the circuit has to be such that you can actually do the source transformations. The other problem is of all the different methods for finding Thevenin equivalents, this one you can only do analytically. In other words, you have to have the circuit diagram to do. The other ones you could do experimentally. You could take measurements of resistances and voltages, etc., to find the model of the Thevenin equivalent. In this case, it has to be done analytically by using the circuit diagram. So we spent a lot of time talking about Thevenin's theorem. Thevenin's theorem was first invented in 1853, and then about 3 decades later in 1883, Leon Thevenin actually formalized it into Thevenin's theorem. Anyway, it was half a century later in 1926 when the dual of Thevenin's theorem called Norton's theorem was invented. Basically, what Norton's theorem says is a very similar thing. Norton's theorem says that if you have two subcircuits, subcircuit 1, subcircuit 2, connected at 2 points, and if subcircuit 1 is linear, as far as subcircuit 2 is concerned, subcircuit 1 can be modeled as a current source, call it ISC, and a parallel resistance called R Thevenin. If you look at it, this is nothing more than the source transformation of the Thevenin equivalent. Because from the current source and a parallel resistance, you can multiply the current source by the resistance to get a voltage source, and put the resistor in series, and you get a Thevenin equivalent model. The resistance is the same, and the voltage source here is now R Thevenin times ISC. So the relationship between the Thevenin equivalent model and the Norton equivalent model is nothing more than a source transformation where the relationship between ISC and VOC is that ISC is VOC over R Thevenin. And by the way, we saw this equation earlier in the VOC-ISC method for finding R Thevenin. What I find incredible is that it took half a century to come up with Norton's theorem after Thevenin's theorem was invented. So to find the Norton equivalent model, there are a couple ways you could do it. One way is instead of finding VOC, the open circuit voltage across terminals, instead you find the short circuit current ISC. Depending upon the circuit, you might find that it's easier to find ISC rather than VOC. That's why you might say you'd rather find the Norton equivalent first. As far as the resistance goes, there's no difference whether you're finding the Thevenin equivalent or the Norton equivalent. You have the same 4 approaches to find the resistance R Thevenin. So let's briefly show how you could find the Norton equivalent of the circuit here. You should recognize the circuit by now. We've used it for many different examples. So now rather than finding VOC, we're going to find ISC. And we actually did this before, but we'll do it again. 20 volts, 5 ohms, 2 amps, 20 ohms. If we want to find the Norton equivalent then, we take these terminals, we tie them together, and we measure the short circuit current between those terminals. If we ground that bottom terminal there, notice this is all the same potential here, and so the voltage all along that ELO node is 0 volts. We can now do KCL here. That current plus that current plus that current plus that current is equal to 0. So doing KCL, we get 0 minus 20 over 5 ohms. That is that current. Current going down is negative 2 amps. Current going down here is 0 minus 0 over 20 ohms. And the current going here is what we're measuring, ISC. Solving for ISC, we get ISC is equal to 6 amps. And once again, we saw this earlier when we used the VOC-ISC method to find the Thevenin equivalent model. So this is just a repeat of something we did a couple lectures ago. Then to find R Thevenin, once again, we did this before already. You turn off all independent sources. Voltage source becomes a short circuit. Current source becomes an open circuit. And then you measure, either analytically or experimentally, the resistance between those terminals. And that, by definition, is R Thevenin. So R Thevenin is what? 20 ohms in parallel with 5 ohms or 4 ohms. So the Norton equivalent model for this circuit is given by that. I should point out, if you look at the example we just did on source transformations, notice we actually got the Norton equivalent before we got the Thevenin equivalent. We didn't cover Norton's theorem at this point, so you didn't recognize it, but here's the Norton equivalent, and then from the Norton equivalent, we did a source transformation to get the Thevenin equivalent. The bottom line is that the Norton equivalent is a very simple extension of Thevenin equivalent. It's nothing you really need to worry about. So this raises a question. Do all circuits have both a Thevenin equivalent and a Norton equivalent circuit? Well, first off, for a circuit to have either a Thevenin or Norton equivalent circuit, it has to be a linear circuit. Remember, Thevenin's theorem doesn't apply if the circuit is not linear. Assuming that the circuit is linear, most circuits will then have both a Thevenin and Norton equivalent, but there are a couple exceptions. For example, when calculating the Thevenin equivalent, if you find that R Thevenin is 0, a short circuit there is no Norton equivalent. A voltage source with 0 series resistance cannot be converted into a current source and a parallel resistance. So circuits that have a model like this do not have a Norton equivalent. Likewise, if you were calculating the Norton equivalent of a circuit and find that there is an infinite parallel resistance here, that circuit would not have a corresponding Thevenin equivalent because you cannot convert a current source with an infinite parallel resistance to a voltage source. So the bottom line, there's a very small class of circuits that have only a Thevenin equivalent and another small class of circuits that only have a Norton equivalent, but that's few and far between. So now that we've finished talking about Thevenin's theorem and briefly Norton's theorem, let's sort of review the 4 approaches for finding the Thevenin and Norton equivalent and see when they can each be applied. So the first method we looked at was the equivalent resistance method. The equivalent resistance method could either be done analytically, if you look at a schematic and simplify it, or experimentally by using an ohm meter. But doing it analytically, combining resistors, etc., may not be possible if you cannot simplify the resistive network. That doesn't mean that it doesn't have a Thevenin resistance. It means that you would have to do it experimentally. Second thing to point out with this first method is if you have active components, by active components we mean dependent sources, you cannot use the equivalent resistance method. The second method we looked at was the VOC-ISC method. Once again, this could be done analytically if you have a schematic. You can analyze it to find VOC and ISC, or experimentally. You could measure the open circuit voltage, you can measure the short circuit current, and then divide those to get the resistance. And we saw that this method is preferable to the equivalent resistance method because you can handle circuits that have dependent sources. However, this method requires you have some independent sources. If you have no independent sources, you cannot use this method. So it's more versatile than the first method, but it's not completely versatile. The third approach can always be used, and that is the external stimulation method. It always works. And specifically, if you have a circuit that has dependent sources but no independent sources, you must use this external stimulation method. And once again, it can be done analytically with a circuit diagram or experimentally. You can take the circuit and apply an external voltage or current source and measure the current through the voltage source or the voltage across the current source. The final method that we just looked at was the source transformation method. Unlike the other 3 methods, this one can only be done analytically. You need a schematic. There's no way to do the source transformation method experimentally. Furthermore, although this method is simple, it's very limited because it cannot work if you have active components. So if you have dependent sources, it doesn't work. Furthermore, even if you only have independent sources and resistors, it doesn't always work if you cannot actually do a source transformation. Once again, depending upon how the circuit is laid out, you may find that you can't do a source transformation to simplify the circuit at all. These 4 approaches are summarized on this chart here. So we have this broken down into 4 different types of circuits. First type of circuit has just independent sources and resistors. So whenever a circuit has no dependent sources, we call it a passive network. So a passive network is one with no dependent sources. Second type of network is one that has resistors and independent sources and dependent sources. Because it has dependent sources, we call it an active network. By the way, both of these networks are also called driven. Driven basically means that it has an independent source. So driven means that it has an independent source. And once again, active means that it has a dependent source. Third type of circuit had just resistors and dependent sources. So it was active because it had a dependent source, but it is what we call source-free, which meaning that it has no independent sources. So terms driven versus source-free deal with independent sources, and the terms passive versus active deal with dependent sources. And of course, the final type of circuit is one with just resistors. So we have four cases, and that would be a combination of passive and active circuits and a combination of driven and source-free. So you notice these four types of circuits cover these four combinations of passive versus active and driven versus source-free. Now if you look at the different methods, the equivalent resistance method, the first method we looked at, only works when a circuit is passive. So it works for the first type and it works for the fourth type, but not for the second and third. The VOC-ISC method requires the circuit to be driven. So it works for the first two types, but does not work for the third and fourth type because they are source-free. The external stimulation method is the most versatile. It always works. It works for any of those circuits. Finally, the source transformation, which is the easiest method, is also the least applicable. It only works when you have independent sources and resistors, and even then, it's not always possible. It depends on how the sources and resistors are combined. So you may find this chart to be handy when trying to remember which method can be used for the different types of circuits. Final topic we're going to look at in today's lecture is the Thevenin equivalent model for circuits containing op-amps. This seems very confusing, but it actually is very, very simple because it's really just a matter of memorizing some results. So what happens when you want to determine the Thevenin equivalent for a circuit containing an op-amp, if we have an ideal model of the op-amp, which is what we do in this class, basically an inspection approach is often the most convenient. And that's what we're going to be doing in our examples on the next page. What happens if you want to use a more complicated model for the op-amp, such as a standard behavioral model, because a standard behavioral model has a dependent source in it, you have to use either the external stimulation method or the VOC-ISC method to find the Thevenin equivalent. But we're going to focus on this first approach here. What is the Thevenin equivalent for some of these ideal op-amp circuits? And we're going to see that the results actually are very simple, and it's just a matter of memorizing them. One final point about Thevenin equivalent of op-amp circuits is that Thevenin equivalent circuits only apply for circuits that are linear. So, if an op-amp is in its saturation region, such as being used as a comparator, the Thevenin's theorem is not applicable because Thevenin's theorem does not work for circuits that are not linear, and op-amp circuits in saturation are nonlinear. So let's come up with some of our simple results. First off, we're going to look at an inverting amplifier. And we want to determine the Thevenin equivalent as seen by the source connected to that circuit. So when you connect an input to an inverting amplifier circuit, what does it see? There's R1, there's a feedback resistor R2, there's also the load resistor RL, but what does this circuit actually see? Using the ideal model of the op-amp, we know that the voltage at the inverting terminal, because of the virtual short circuit approximation, is the same as the voltage at the non-inverting terminal, or 0 volts. And so it doesn't take much to see that all that Vin sees is a resistor R1. So the Thevenin equivalent circuit, as seen by Vin, is simply R1. It doesn't know what R2 is. It doesn't know what the load resistor is. It doesn't know that it's connected up to an op-amp. All that it sees is R1 going to ground. And so the Thevenin equivalent, from looking at the input, is just that external resistor R1. Let's look at the same inverting amplifier circuit, but now let's find the Thevenin equivalent as seen by the load. So once again, if you stick a load up to an inverting amplifier circuit, what does it think it's connected to? Well, we already know that the voltage here is independent of the load resistor, and its value is what? It's negative R2 over R1 times Vin. Since the voltage that that load resistor sees is independent of itself, this means that the Thevenin resistance has to be 0. So the Thevenin equivalent circuit as seen by the load resistor is nothing more than a voltage source, and the voltage source's value is minus R2 over R1 times Vn. Once again, the reason that the Thevenin resistance has to be 0 If the Thevenin resistance was not 0, changing your load resistor that you put here would change the voltage across the load resistor because of voltage division. Because we know that changing the load resistor does not change the voltage across it, we know that the Thevenin resistance of the op-amp circuit has to be 0. So now let's look at a difference amplifier. So now we have two different inputs, VA and VB. So first we want to see what the Thevenin equivalent circuit is looking from the point of view of VA. So this is similar to the inverting amplifier. We first have to find the voltage here, and from there we can immediately see what VA input sees. The voltage at the inverting terminal is the same as the voltage at the non-inverting terminal, which we get from a voltage division. It's R4 over R3 plus R4 times VB. So that means that V minus is R4 over R3 plus R4 times VB. So that means that all that VA sees is this resistor R1, and then it sees a voltage source equal to R4 over R3 plus R4 times VB. So this is the Thevenin equivalent circuit as seen by the VA input. How about VB? What does it see? Once again, because there's no current flowing into the non-inverting terminal of the op-amp, all that VB sees is these two resistors, R3 and R4. So that's an even simpler model. The Thevenin equivalent circuit as seen from the VB input is just the sum of R3 and R4. So that's basically all we need to know about the Thevenin equivalent of op-amp circuits. I should point out that if we were to use the standard behavioral model for the op-amp rather than the ideal op-amp model, the analysis would be much more complicated. But once again, if using the ideal amplifier, you can almost get from inspection what the different inputs and outputs of the circuit see. Next class, we will finish our discussion of the Thevenin's theorem by talking about loading of circuits and something called maximum power transfer, which is a very important application of Thevenin's theorem. Have a good day.